In early 1996, the FDA approved a revolutionary new HIV drug, and immediately Abbott Labs began producing it for tens of thousands of HIV-infected people, and for 240 lots, drug tablets were produced without incident. Then in early 1998, a new form of the drug spontaneously appeared, and it rapidly spread through the whole factory, cutting off tablet production. Sounds like a science fiction story, right? In this video, we look at the curious case of the transforming HIV drug. This video is brought to you by the Asianometry Patreon. It's one of the better ways to support the channel. Early access members get to see new videos first and selected references too. It really helps me a lot and I appreciate every pledge. Thank you, and on with the show. When we take a drug, we take in an active pharmaceutical ingredient. It's not enough that an ingredient works against an infection. We also have to ensure that the drug can get to where it is needed and stay there until the threat has passed. These active ingredients are simple organic or inorganic compounds, and like with everything else, they can exist in a number of different solid forms. Such forms can be wrapped up in a tablet or capsule for consumption. One solid form or state is amorphous, which, as the word suggests, the active ingredients as molecules are jumbled about without any clearly defined shape. Another way is as a crystal. A crystal is simply where molecules are arranged in a well-defined orderly lattice. These crystals can be formed from a liquid solution or a melt. For instance, think about semiconductor manufacturing, as I sometimes do, and the famous Czochralski process. We make the big honking silicon crystals for chips by dipping a seed silicon crystal into a melt and slowly pulling a larger crystal out of it. Not quite the same as what they do in the pharmaceutical factory, but you get the idea. The funny thing is that there is more than one way to arrange a crystal. In 1821, the German chemist Eilhard Mitscherlich discovered that by simply rearranging how the molecules crystallize, you can end up with very different things. Look at the minerals aragonite and calcite. Both are made from calcium carbonate, but have different physical properties like melting points, densities, hardness ratings, or solubilities. Mitscherlich called this polymorphism. Another example is glycine, the famous amino acid which can crystallize into a prism or pencil shape. Polymorphism might not affect the drug's fundamental effectiveness, but it can affect many practicalities. Like if people are taking tablets or capsules, a different polymorph can affect the tablet's texture, shelf life, stability at room temperature, stability when exposed to light or air, so on. So pharmaceutical manufacturers need to pay special attention to polymorphs. Troublingly, polymorphs are not necessarily stable. One can transform into another when the conditions are right. For some polymorphs, though, those conditions are so rarely achieved that the new polymorph might not be known for a long time, decades even. Take aspirin. We first isolated this drug over a century ago, but it was not until 2004 that computer simulations predicted an extremely rare second polymorph of the drug, aspirin form 2. A second round of experiments a year later proved those simulations correct. Aspirin form 2 is rare because it does not take a lot of energy for it to reconvert into form 1. Fortunately for us, form 1 of the drug is the one we are most familiar with and want. What happens, though, if that is not the case? HIV is a virus. If left untreated, an HIV infection will eventually develop into AIDS, a generally unwanted condition. To prevent this, people take antiviral drugs. The first HIV drugs to hit the market were the nucleoside analog reverse transcriptase inhibitors, NRTIs. AZT is the most famous of these type drugs. NRTIs block the virus's reproductive process initially, but unfortunately the virus eventually develops a resistance to this mechanism. Thus in 1995, a new class of antiviral drugs emerged with a different mechanism, the protease inhibitors. After infecting a T cell, the HIV needs to reproduce. Thus, it forces the cell to create a long chain of proteins. That long chain needs to be chopped up into smaller ones. This process allows new viral particles to mature and become infectious. To chop, the virus uses a special enzyme called the protease. The idea of the protease inhibitor, then, is that if we can somehow mess with HIV-1's chopping knife, reproduction can be stopped. New viral particles never mature and cannot infect. This class of drugs also makes an appearance in my video about hepatitis C. They were quite effective for that virus as well, though with drawbacks. Protease inhibitors were a significant breakthrough in the fight against this accursed virus. The first such protease inhibitor to hit the wide market was Ritonavir, developed by Hoffmann La Roche and approved by the FDA in a record 97 days, an indication of its groundbreaking nature and the desperation of the situation. However, one issue with these early protease inhibitors was that they were either poorly absorbed through the intestines or quickly flushed out by the liver. Only 4% of Ritonavir is absorbed by the body. But more protease inhibitors were on the way. In 1982, Abbott Laboratories, now AbbVie, noticed that the HIV protease enzyme resembled another enzyme they were then researching, renin, which has blood pressure implications. The scientists began to re-engineer the work they had been doing to block renin to now block the HIV protease. They crafted a molecule that not only fit the protease's unique shape to disable it, but also can be properly absorbed into the bloodstream. Using computer-assisted design, the team generated hundreds of possible candidates, and in 1992, 3 candidates were chosen for development. 2 of the 3 fell short in tests, but the third, ABT538, which Abbott eventually named Ritonavir, showed instant results. In December 1995, a human study showed the drug to be quite effective, significantly reducing patients' viral load of HIV-1. White blood cell counts rebounded as well, nearly doubling. Patients tolerated the drug quite well, with the worst adverse effects being diarrhea, nausea, and headaches. Despite concerns about potential drug resistance, it was concluded that Ritonavir can delay the virus's progression and extend people's lives. After the news went public, Abbott announced that it would give away 2,000 doses to late-stage AIDS sufferers. Since supplies were so limited, Abbott set up a lottery in the United States to decide who will receive it. In March 1996, the FDA's advisory panel recommended the approval of Norvir, Ritonavir's commercial name. The name was chosen after senior project leader Dan Norbeck. Abbott began ramping up production in January 1996 before approval was even granted. Demand was incredible. Canadians traveled to the U.S. to get it, and 224 bottles were once stolen out of Abbott's Canadian offices, fueling a fervent black market. The protease inhibitors were combined with other existing drugs to make up the core of what we call highly active antiretroviral therapy, a revolutionary combo of drugs that today makes HIV infection a managed condition rather than an automatic death sentence. About 2 years into Ritonavir's entry into the market, the people at Abbott's factory in Chicago noticed something. Ritonavir is sold in 2 formulations, a liquid and a semi-solid capsule. With the latter, the drug is dissolved into a semi-solid wax-like substance that fills the capsule. Unexpectedly, in early 1998, the capsules started failing their dissolution tests. In other words, the capsules were not dissolving as expected. The drug was also precipitating out of the capsules, meaning that after we dissolved the drug into the waxy stuff and put it inside the capsules, it did not stay like that, but instead separated into solid crystals. Abbott's researchers looked at the capsule's contents under a microscope. They expected the Ritonavir crystals to look like rods or long rectangular blocks, stretched and flat. But these Ritonavir crystals looked distinctly different, a cluster of very fine needles. They then ran an X-ray powder diffraction test, which is often used for identifying a material's crystal structure, and it confirmed a new, previously unknown crystal polymorph, Form 2. The Form 2 polymorph is more thermodynamically stable than Form 1, and that is its fundamental problem. Because all of its hydrogen bonds are satisfied, Form 2 is 5 times less soluble in the ethanol water solutions used to produce the original capsules. Thus, the Form 1 manufacturing process cannot be used with Form 2. Troublingly, this polymorph can spread. The tiniest presence of Form 2, even a seed of just 1 part per million, can cause all the Ritonavir in an area to crystallize as Form 2 rather than Form 1. Abruptly, Form 2 took over the Chicago factory's entire output. Then, a team of scientists who had been exposed to Form 2 traveled from Chicago to another Abbott factory in Italy so to investigate possible manufacturing process changes. But soon after, that Italian factory's Ritonavir started coming out as Form 2 instead of Form 1. Coincidence? By July 1998, drugstores began running through their existing supplies of the old Ritonavir capsules. Abbott held regular press conferences to update the public, and the transcripts seemed to convey some truly strange happenings. Quote, "There was no gradual trend. Something occurred that caused a new form to occur. There was no early warning. We did not know how to detect a new form. We did not know how to test for it. We did not know what caused it. We didn't know how to prevent it. And we kept asking the question, why now? We did not know the physical properties of the new form. We did not know how to clean it, and we did not know how to get rid of it." Since skipping doses was unacceptable, Abbott provided the liquid formulation of the drug to the 70,000 patients relying on it for their drug cocktails. The liquid version of the drug worked the same, but it tastes bad. Like, really bad. Some patients even called it vile. Treatment advocate Dave Gilden said, "It's like awful liquor that makes your mouth and gut tingle and sting the whole way down. I kept burping it up." Abbott can only advise that people mix this vile liquid with chocolate milk or ensure nutritional drink. Other top chasers, as suggested in a survey conducted by Abbott's marketing department, included oats and honey granola bars, toast crackers with peanut butter, and Nutella. Nutella makes literally anything taste better, doesn't it? There were also some other concerns. It is 43% alcohol, which can cause issues for alcoholics, and the liquid format might not hold up as well in warmer temperatures, so shelf life and storage requirements also had to be modified. As supplies of the capsules slowly ran out, a team of hundreds of Abbott's scientists were assigned a dual-pronged approach to fixing the issue. First, they started working on a solid formulation for the Form 2 variant of the drug. Second, they simultaneously began investigating a new pathway to consistently produce the Form 1 again. In the latter, the Abbott team went to great lengths to find a new way to get the Form 1 line back again. An excerpt from an update press conference goes, "We tried everything. We conducted countless experiments. We reconditioned our facilities. We rebuilt facilities and new lines. We looked at alternative sites. We visited a number of other organizations around the world to see if we could start clean in a new environment free of Form 2. In a matter of weeks, maybe 5 or 6 weeks, every place the product was became contaminated with Form 2 crystals." Abbott scientists eventually found that they can produce Form 1 again so long as the solution and the reactor was not contaminated with Form 2. In the end, though, they decided to move on. After all, Form 2 seemed to be the one nature quote-unquote preferred. At a press conference, Abbott research scientist Dr. Eugene Sun declared somewhat dramatically that we will never be able to go back to Form 1. Once the existing Form 1 capsules available at wholesalers are used up, it will be gone, supposedly for good. Prior to the emergence of Form 2, Abbott had been working on a soft gelatin capsule for the drug. When it became clear that Form 1 wasn't coming back, Abbott quickened development of the soft gel capsule to see if it can be filled with Form 2. In March 1999, the company began working with the FDA to get approval for this new gel capsule format. This took a few months as studies had to be done, but by July 1999, the FDA approved the new gelatin capsule, essentially ending the crisis. The company estimated that $250 million in potential revenues were lost during this year-long saga, not to mention the cost of having hundreds of Abbott employees give up their summers and vacations to work on this 24/7, a costly lesson. Much later, scientists discovered ways to convert Form 2 back into Form 1, though it takes time and careful effort. And later in 2010, a way was discovered to make Form 1 capsules again using a hot melt extrusion method, basically where you melt the stuff and then shape it with a template. Researchers eventually discovered 3 more forms of this drug, so 5 in all. Interestingly, Form 3 forms when the drug is exposed to a liquid solvent, and if you expose that form to water, it then turns into Form 5, and Form 5 can then be converted into Form 1, a convoluted way to find Form 1 again. One final question, though, is where did the Form 2 come from? The answer is not all that clear. Form 2 spreads extremely well, but it is not particularly easy to spontaneously create. Abbott produced Ritonavir by coupling together 3 intermediates in a series of assembly steps, almost like bolting the wings onto a plane. That process had not recently changed before Form 2's emergence. Though it should also be noted that the molecule's size and complexity is likely why Form 2 was not discovered at the start. There are so many different possible arrangements available. Anyway, the conclusion by Abbott scientists at the time suggested that a manufactured lot of Form 1 Ritonavir had its liquid solvent dried up somewhere in the manufacturing cycle. This creates a certain residue. That residue can then crystallize into Form 2, which then contaminated the equipment. A later paper also suggested the idea of milling. A team discovered that mechanical action with or without the presence of liquid can cause Form 1 to spontaneously transition into the first seeds of Form 2. Of course, it is too late to confirm. Issues with crystal polymorphism continue to bedevil the pharmaceutical industry. In 2008, just 10 years after the Ritonavir thing, the curse struck again. There's a Parkinson drug called rotigotine, marketed as Nupro, thank goodness, because that name sucks, which is normally applied as a patch. The drug abruptly developed a new crystal polymorph which crystallized on the patches, reducing its effectiveness. Just as before, the whole thing had to be withdrawn and reworked. The disappearing polymorph story sounds like it comes right out of science fiction. And famously, the Kurt Vonnegut book, Cat's Cradle, has this thing called Ice 9, an ice polymorph that converts all the world's liquid water to Ice 9. The Ritonavir saga is not quite as dramatic. I don't think it's going to end the world. But it's a real concern for pharmaceutical companies going through manufacturing ramp-up. It is also a fascinating reminder that nature always has something new to throw at us. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.